ML of the population mean is the sample mean, and the ML of the population variance is not the sample variance, but 1 over n sum xi minus x bars quantity squared. And so important result is that the ML for the mean is a t distribution, has a t distribution when you normalize it, and furthermore, n over sigma squared times the ML of the variance is a chi-squared with n minus 1 degrees of freedom. So what we're going to do today is we're going to find 95% CI for mu and sigma squared for normal data, and we'll show that that involves the t distribution and the chi-square distribution. And we'll also do a parametric bootstrap in R to find a confidence interval, and we'll also introduce you to some large sample properties of the ML estimator, also as an attempt to get a 95% CI. So just very quickly, we've sort of done this before. So for the population mean, now I'm not assuming that I know the population variance. So when I standardize, the SD is approximately S over square root of n, which gives rise to a t distribution, which is why my confidence interval involves a t distribution instead of the z distribution as we had in chapter 7. When we do the confidence interval for sigma squared, so the sampling distribution for n over sigma squared times the ML estimate of sigma squared is a chi-squared with n minus 1. So we have this distribution here, and we go through the usual tricks, algebraic manipulations, and we get a formula highlighted below for the CI of sigma squared. Okay. So next, let me tell you about parametric bootstrapping. So first of all, if we just review what a 95% CI is, so we have some sampling distribution for our estimator minus the parameter, which, because we don't know the parameter, we estimate it with let's say our mom estimate for our original sample, and then we take many samples. We take many samples, let's say 1,000 of them, find estimates for all of those, and that's what we'll call theta star. So theta star minus theta hat is an approximate sampling distribution for what's really theta hat minus theta. So the formula that we derived before, I believe it was lecture 5, is the formula for 95% CI of theta. And notice that B, which is the 97.5th percentile, comes first. So it's theta hat minus B theta, and then theta hat minus A. In R, you can find the 97.5% quantile, so you can find that using the quantile command, and so this would be so theta star minus theta hat is your list of 1,000 numbers, and alpha here is 0.05. And similarly, you can find A, and then your 95% CI you can write as 2 theta hat minus the quantile of theta star and then this vector here. Okay, so what's a parametric bootstrap? Well, so the difference from a non-parametric bootstrap is that instead of resampling 1,000 times from your sample, you're going to be really confident about what your probability model is, and you're going to randomly produce 1,000 samples using R to randomly generate the distribution. So step 1, we get a sample, we make a histogram and guess a model that fits the histogram. 2, we're going to estimate the parameter using a MOM estimate. And then we're going to overlay the histogram from step 1 with a frequency plot for the model distribution with the estimated parameter. And finally, we're going to use the model with the estimated parameter to generate the sampling distribution and find its SD. So we did an in-class exercise. I sort of cheated and generated my data, my original sample. I wanted it to be Poisson, and so I was lazy. I didn't hunt around for data. I just created it randomly. So that's my data, which I cheated. Sorry about that. And so I make a histogram of it. It looks Poisson to me. So I found a MOM estimate for it, because I know that the MOM estimate's just the sample mean. So I computed the sample mean, I got a MOM estimate, and then here theory, theory is now going to be I'm randomly generating my Poissons. So I did this so that I could check that indeed it's a good fit to the data. And then, so I'm going to do this, I'm going to replicate this process 1,000 times and find the SD of that list. So, so you can compare this with non-parametric bootstrapping. Here, just notice that you're sampling here with replacement. Then I'm calculating a CI now. This is for a different problem for gamma. This, I'm not showing all the code here, but we had some precipitation data, and that was our sample. We calculated the MOM estimate for alpha and lambda, and then so here I'm just following I'm following the process of finding a CI. So so here this function, I'm replicating it many times, and in this function here, notice here this arrivals. See, I'm randomly generating a gamma distribution many times. So it's because I'm going to replicate this b times, so I'm generating this many times with a particular alpha and beta MLE that I calculated in earlier, and so I have my model probability. And so then the other highlighted portion here is just the confidence interval using the formula that I showed you above. On to large sample theory for MLE. So essentially MLE, the main theorem is that the MLE for theta is asymptotically unbiased and normal. So theta hat for large sample size is approximately normal, unbiased, so the expectation is just the true parameter, and its variance is 1 over n times the sample, n times the Fisher information. And so this Fisher information is what we're going to talk about for the rest of the time now. So what does the Fisher information measure? Well, basically it tells you how useful your random variable is, your data, to determining theta. So for finding an estimate for theta. So let's look at the log likelihood for two circumstances where our data is very informative and very uninformative. So for the informative case, I'm going to have x be normal mu1, in which case the log likelihood is a downward facing parabola, and an uninformative one where the variance now is 25 instead of 1, and I also have a downward facing parabola. So so I'm going to plot these log likelihoods for 1,000 different x's, and that's going to give me 1,000 different trajectories. But to make this concrete, since these are functions of our parameter mu, the true value will let equal to be 5, and so we get something like this. Okay, so these are these distributions, these log likelihoods, and so here you can see that. Well, let's put these together if I can. So so in the top one, you can see that the peak of the arch is something between 3 or 2.5, or yeah, it's somewhere between, let's say, 3 and 7. Whereas for the bottom one, it's in a much wider range. So the data for in the first one is much more informative for finding the true parameter, because we have a much smaller range of values to check. So now, each curve here is sort of providing their own vote for what the true parameter location is. And so we are going to introduce the score function, which is the derivative of this log likelihood. So this is going to give us a measure of how pointed the trajectories are. So we're going to pick a few values of mu, and so here we're concentrating on the log likelihood with for the uninformative one, and so the top picture just shows for 3 different mu values, and so what you can see in the picture below is the range of slope values for the blue, green, and red is becoming increasingly negative. It's positive, then it's neutral, then it's negative. And now I'm gonna, on the right, I'm making histograms of what of these different scores, and let's concentrate on the middle green one. What you can see is that in the middle green one, it's centered at 0. There's some negative scores, there's some positive scores, but it's a fairly nice distribution. So the question is, if we took the informative case, how would the histogram compare? I'm talking about the middle histogram. Well, it would be wider, right? Because having it more peaked would mean that on the left side we would have steep. We could have some very steep uphill slopes, and we could have some very steep downhill slopes to the right of the middle. So the histogram would be much more spread out. We could get some very negative score functions and some very positive score functions, but it would still be centered at 0. So that's the main idea. What we're going to do is essentially look at how spread apart the histogram is, and this middle histogram here, which is centered at the true value, in this case mu is 5. Okay, so we will continue this next time. Have a great day.